Cool. So I'll share a screen. I'll start with the moment. Can you see the screen?
Yes, it's Squid Crimson status.
Yeah, yeah. Not too much slides. Just I'll start by going over the current status we have in Squid for context. So we have multi-core support for Reactor and both for the messenger. We also support mainly RBD workloads on replicated pools with the backends of BlueStore, CStore, and CNStore. We also support quick deployments via Ceph ADM, Rook, or Restart by quick, meaning in previous releases before Squid, we had to actually manually set the resources, speaking on the CPU cores, that OSD is allowed to use. By now, we also have a more automated way to deploy a cluster without manually specifying the resources for each OSD. We also have initial scrub support. We can initiate it via the Ceph tell command for scrub or deep scrub. Scheduling, repair, and other features of scrub are future work, and I'll mention that in the end. And lastly, recovery and backfill. We put a lot of effort into stabilizing recovery and backfill pattern and edge cases. A lot of thanks to Shuan from the Intel team, who I think is here. So we are in a much better state. In terms of test coverage, we have our stable suite, which we will probably need to expand. I'll also mention that. We gate PRs against it, same as Classic, SenseRith, help us to avoid any regressions. And we added recovery trashing patterns, as I said earlier. Now that we support it better, we introduced much more complex tests into the suite. And lastly, we also added CStore as a backend, which is really cool, to the suite. And it's mostly able to pass all the APIs test and a basic test, which is a great milestone. And another cool, interesting thing we have in Squid is coroutines. This is more of should allow us to develop much more in a friendly way. This is how the CPP20 introduced coroutines. This is how the code from the client request used to look before coroutines. This is after coroutines, so it should help us make the code a bit more friendlier and fasten the developing progress. And lastly, I'll start going over the next steps / features we are planning for the T release. So the most, I filtered out the Crimson ones. For CStore, we have Inkshin, which will introduce some of those later. But we have the link in the Etherpad for all the features without the filtering. So the most relevant ones, I guess, are supporting Erasure EC pools. This is work being done by Radek, almost done, actually. It should be there in T release. PG splits, dynamic PG splits or merges. For now, it's only static. Aishwarya is working on that. And as I mentioned, Scrub is only there as initial kind of support, mostly for test. We can test in the end of tautology jobs. So we should be able to support it in more automatic manner. We also added the tracker to which we're planning to support mclock. Now we have a basic WPQ scheduler. Mclock implementation is not yet there, so this should be also quite important. And the last two are automating CPU cores allocation when deploying with Ceph ADM. As I mentioned, in the beginning, we needed to specify the resources for each OSD. Now it's being done in a more automated way, but still we need to do it in a more orchestrated and smarter / elegant way. And this is also something we should focus on in the next release. And lastly, it mentions RBD mirror testing, but it's mostly expanding the suite in general. Now that we are somewhat confident in the suite we have, it's quite minimal comparing to the classical OSD and the client test we have. So we should probably expand it by great magnitude. So these are the features, but I guess for Tentacle, the most important focus is pushing towards performance improvements. Now that we have multi-core support stable in there, now that the workload we know we support is also there, we should really put a lot of effort into performance and performance. We have, this is also in the Etherpad. I guess I can stop sharing for now, just opening the Etherpad. I'll share it instead. One moment. Should be able to view Chrome. Can you see it?
Yeah, we can see it.
Cool. So I added a link for the performance focus we had until today. We tend to label PRs as Crimson Perf to track this more easily. And this effort started already in Squid, and we should focus more on that now in Tentacle. I guess that's it for the main kind of features / plans. We should have Inkshin on the call, if I'm not mistaken.
Yeah.
Cool. So Inkshin is from the Intel team. He's the tech lead of the C store. And he will present us, I guess, some performance status / C store plans. So go ahead, Inkshin. Thanks for joining.
Yeah, I'm trying to present. Sorry, I'm not familiar with Google Meet yet.
It's okay. I can also try to share the slide if you. I think I have it also. So if that's a problem.
Can you see my screen? Can you see my screen?
Yes, I think I see CDS Crimson slide.
Yeah.
Okay, so my name is Yingxing, and I have two things today. The first part is performance evaluation, or the first part is the performance evaluation about to understand where we are right now, and the second part is C-store status and the plan going forward. Yeah, feel free to stop me if there are any questions. So first of all, the summary is that I think the most important, or the basics of the performance, is the end performance of the RBD 4K random reads and writes with C star, which will represent the basic performance characters of the Crimson OSD. And a second aspect is that because we are talking about the core scaling properties, the issues that Crimson is going to address, so that angle may be an interesting way to see how the current design works even without the end performance available. And we already have a lot of optimizations merged in the Crimson, and which is labeled with the Crimson Perf tag. And I think all of them can be categorized into three categories. The first is the compute efficiency, which is to optimize the algorithm directly and optimize based on hotspots remove unnecessary memory copies or calculations, which was maybe too simple to maybe implemented too simple. And the second category is the I/O efficiency, which is mostly about to reduce the read amplifications and the write amplifications. So we will see less disk read and writes from disk level. So to make it less likely to be I/O bounded. And the third issue may be more complex because it is related to starvation or internal contention. And although that with the architecture of Crimson, each core will running independently, so it might be unlikely for different cores contention on each other, but it is still quite likely because we can still couple CPU computation and also I/O behaviors in the same lock. And so we can still need to, if we see that the Crimson, we cannot, there's no apparent I/O bounded issue, or the CPU is not very busy, so we might be the issue might be related to starvation. So we'll need to think about there might be some locks which is too coarse-grained, or there might be some issues related to cross-core implementations. Maybe it's not very efficient. And also there might be, it is possible that the different shards are running not very balanced. Some shards is running 100% using 100% CPU, but the other shards isn't very busy. And also that might be related to some background tasks. And also for the performance considerations, there might be some special considerations. For example, even though we might not be able to prove the performance, the end performance with random read and write, we can still focus on the metadata intensive performance, because C-star has its own implementation of the indexing. So there might be a lot of opportunities to improve such performance related to a large scale of port deletion, recovering, and very small objects, operate on very small objects, etc. And it is also possible to implement, and it is already implemented, the store level device tiering to make SSD and HDD work together. So SSD can be act as the hot tier to absorb the most intensive IOs, and HDD can be, and when the data or metadata becomes cold, it can be moved to HDD, so the entire solution can be more efficient to doing that, because we can do a lot of possible things to achieve that. And also C-star can be implemented to optimize not only on the sequential disks, but also optimized for the optimized for random writes for SLC. And also C-star is pretty much optimized for the ZNS behavior. And we have evaluated the first part is the one important part is the scaling, core scaling behaviors, and we can start from simple. It's start from messenger messenger-to-messenger performance tests, and from these tests, we can see that compared with the async messenger talk to each other, and where there are more cores added to the workload, it is the trend is the Crimson performance is more scalable when adding more cores. So this proves that the architecture is working as expected. And also, if look at the right side to evaluate the hotspot of when the messenger is running on one core and on more than 100 cores in the same using the same process, the internal behavior is almost identical. So which means that when adding more cores, each shard will work pretty independent. So that's why the performance can still grow with CPUs. So which is also the goal, the design goal of the Crimson. And we also extended the tests with OSD. So we use Rados Bench to test Crimson OSD with CInstall, which is memory based, and also evaluate the test performance with classic OSD with memstores, so we can basically understand the similar trend when adding more cores, if the end performance can scale with cores. And it seems to me that it follows a similar pattern both in read and write. When adding more cores, the Crimson upper part of the performance can grow more scalable here with even with 24 cores or 32 cores. I think it shows that at least with Messenger and OSD, the scaling property is very good. And the most important part is still the end performance. So the first, the left side is evaluation with Crimson C star versus classic Blue star, and use a simpler client using the Rados Bench 4K read, because using Rados Bench, the behavior can be the behavior can be quite straightforward, because if client issues 4K I/O, it will directly translate it to the Rados object layer. So it is more easier to reflect the raw performance of the OSD, I think, and the performance is also seems like looks like that when adding more cores, the performance, the Rados Bench read performance of the Crimson Plus storage can grow much faster than the classic. And we also found that this trend, we cannot reproduce this trend with the current min. And we also identified that there is a read amplification related issue, and we were working on the optimization. And after that optimization, and this is still an ongoing PR. So we combine this PR and also add the onto the Crimson C star, and it seems that we can successfully the performance characters can be on the left side can be successfully reflected to the FIO RBD workload. So with the fine-grained cache PR, And the 32 cores, the Crimson C Star has a much better performance, read performance than the classic Blue Star. And that's pretty much what we can see about the advantages of the Crimson stack solution. And last year, we have a lot of PRs related to the optimization. And if we evaluate the current performance versus the original, probably 1 year ago, the performance has improved a lot. So, but there's still some work to do to further do further improvements. Okay, so that's all about the performance part. And the second part is C-star status. As of the Squid release, the core features of C-star is already functional, which includes the data read and write, and the metadata indexing include to index Rados objects and the object data and the metadata and the logical block address translations, and also the critical features, including the transaction support and the background tasks are also fully implemented and working. And other features, including the snapshot and clone, and the basic hot and cold device tiering, and the supports for the both sequential reads, sequential writes, and random writes are also implemented. And the C-star can now working with multiple CPUs, and also the read checksum is also supported. And we also enabled the basic test suite in the topology, so we are testing against it for every merge operation. So it's pretty much the current C-star status. And for the path forward, I think the most critical part is still the correctness and the maintainability, because we need yes. So the basics is that the implementation must be correct, and we are able to keep maintaining it, so it doesn't break because of complexity. And also the performance is critical to convince the users to use the Crimson and also C-star. So it will include a lot of efforts to monitor, to do performance monitoring and a diagnosis of the current issues. And I think the basically we need to optimize based on the random 4K block read and writes, and to prove, in order to prove that those optimizations are good. And for the ongoing features, there are some, I have listed some features here, and the first one is periodical status reports, which is I'm working on, and I want to implement the basic monitoring and diagnosis implementations to report the C-star internal behaviors, including the disk level and the cache level, and also the background tasks, which is tracked by this tracker. And another important optimization is the fine-grained cache, because without that, there will be a significant read amplification, which will causes the read performance to be I/O bounded, because if we don't implement the sub-extent level cache, when we write 4K, for example, a very large extent, we need to read the entire extent out to access the for example, 4K range of the extent. So this is very not very efficient, and making the FIO RBD workload bounded by the I/O instead of the CPU. And another ongoing feature is the 128-bit logical block address support, and which is to extend the current logical block address range from 64 bits to 128 bits. This is mostly because that 64 bits logical block address range is very insufficient, and if the logical block address range is mostly occupied, it will introduce severe performance issues because when the address space tends to when the address space is almost full, and there will be much more efforts to find the empty slots, and there might be higher probability to have transaction conflicts. And another feature here is about more efficient device tiering. This is the bucket level RU cache in the hot tier, which is related to the hot and cold device tiering, because if the data in the if the data or metadata in the C store doesn't get modified, it will be naturally be cooled down and will become the code data, and will be moved to the code tier. But when there's a lot of access to the code data, and when the memory is not sufficient, we might need to consider to move some data from the hot tier to the from the cold tier to the hot tier, because the hot tier will be backed by more performant devices, and that device will be cheaper than the memory. So it will be very useful if some code data, if get frequently accessed, it can be moved to the hot tier. And the next is a missing operation. C star haven't supported it. It is a clone range 2 support. And another missing feature is that the currently a multi-sharded C star, each C star shard is statically binded to a specific CPU. So currently C star cannot restart with different number of CPUs, because the current implementation of the CPU binding, the shard and CPU binding is static. So if we are going to support dynamic, if we support a feature that we want to restart the Crimson OSD with a different number of CPUs, we need to decouple the C store shard with the cores. So that's the goal of this feature. And also the current multi-sharded C star is implemented based on static sharding. So each shard will the disk space of each shard is statically allocated. So it is not accepted in finally accepted. So we will need to implement runtime disk space rebalance across the shards. And there are still some contributions related ongoing regarding to the random block manager, which will be used by the SLC, and also the ZNS backend. And also another feature missing feature is that the current read checksum is done on the extent level and not the block level. So if we need to enforce the read checksum, the read amplification issue will still be there. So we will need to implement block level read checksum to finally support the sub-extent level read. And also, I think currently C-Star doesn't have implementations to handle disk 4, so maybe there will need to be some implementations there. So that's all from my side. I see a question. I'm not understanding.
I mean, I'm not informed enough about C-Star to have a real opinion here, but why do we need 128-bit addressing? Like, 64 bits is definitely more space than it's ever going to be in a single device.
It's because there's a bunch of locality properties associated with how you want to group blocks, and we ran out of bits.
Okay. So we're
we
stealing portions of the
reserve,
space for other things.
we reserve some bits for the core or for the crash. So it turns out the space is not sufficient for the object part.
Yeah, it's not that there
okay.
are more than 2 to the 64th objects, Greg. It's that
Yeah.
we need to represent like the crush hash and the other properties of the objects that they sort in the right way.
Cool. Thank you.
Thanks, Ingjing, for presenting that. I guess if anyone has any questions or suggestions for what we've discussed, this is the right time. Unless not, I guess that's all we've planned for today. Going over T-plans, the performance overview. So I guess we can wrap it up earlier unless we have any objections. And again, thanks for joining.
If any of you are interested in contributing to Crimson, as you can see, there's lots of unassigned tickets. Feel free to reach out to Matan or any of the developers. That's all I had to add, Matan. Thanks.
Cool. Right. Yeah, we have a Slack channel and a weekly meeting. And we tend to post all the missing bugs/features in the tracker. The link that was sent in the Etherpad is only for features, but we have tons of, I guess, more smaller kind of bugs and missing implementation that we still need to implement. So yeah, feel free to join /ping me. Yeah. Thanks, Nia.
I had just a quick question. I might have missed it because I'm context switching here. So on the slide that showed the difference between the two messengers, there was really a staggering difference in terms of scaling there. And it said that the thing that was varied was the number of cores. So was the classical messenger kind of still using the same number of threads? Like I think it's 3 by default, right? And you simply increase the number of cores, or did you also increase the number of threads there?
Yeah, I also am aware that async messenger cannot really increase the threads to 45. So I also modify the async, the related implementation so that we can configure this number of threads of async messenger to a much larger number. So yes, the async messenger is the threads of the async messenger is also increased.
Okay, yeah, that's really impressive then, because I didn't realize there was so much shared state there between these workers that makes it, effectively useless after 8 cores or eight threads, I guess.
Mhm.
That's
Yeah.
a data point that I didn't realize. I didn't realize it was so bad.
Yeah, so it's I think it's pretty easy to reproduce this test, so we can evaluate that issue using that.
Is
Well,
this
I
a
don't
one-to-one test?
Oh, sorry.
Is this like a single endpoint to another single endpoint test? Because like we have clients that push far more like IOPS than that through async messenger now.
It's only ping pong messages. It's about the messages. It will be the 4K IOPS. The here is about the number of messages or roundways that is a round trip from the if they are classic messenger and classic messenger, they each send ping pong to each other.
Right, but I mean, this looks like you're saying that with one thread you're getting 1,000 4K IOPS out of classic messenger, or sorry, with one CPU, and I mean we have RBG
No,
tests
that's
where it does like
normalized.
It's
Greg.
normalized.
Okay.
Yeah.
With one core, you get one IOP.
Okay,
This is the multiplier over what you get with one core.
okay, gotcha.
Is there any particular reason that you chose to normalize the IOPS rather than just actually reporting the number of IOPS?
I think normalized will be easier to understand the scaling trend. So if we have 54 cores, the performance will be multiplied by like 40. So that can reflect the ratio.
Yeah, it makes it very difficult for me to tell when I look at this whether or not the IOPS that you have for the async messenger actually match expectations.
Yeah, I can also share. I think I can also find the absolute number, but I need to find it out.
We can also replicate it probably on one of our CPL lab machines, more performant ones. But I guess the reason to normalize, as I wrote in the chat, is not to be that hardware should not matter here. It's just to get a larger sense of the results.
Yeah, I'm not sure if I'm missing some important configurations, but it seems to me they are not very much to tune, except from the number of async worker threads for the classic.
Yeah, it's not really a question of tuning. I just want to understand what we're seeing.
Okay, I think I need to
I mean,
find out.
we don't run a
it.
lot of tests with more than eight cores devoted to something like messaging, so it's not unreasonable. I'm just surprised.
And I don't think people, or at least I haven't seen people tweak the config option that relates to the number of async messenger worker threads. So it's probably like the default of 3 is probably like pretty universally deployed. or like I could be wrong. Maybe some people do it, but I just haven't seen in any of the kind of dumps or source reports that I've looked at.
We do it a little bit at Clyso. There are situations in which lowering the number of async messenger threads can be beneficial. And we do see that sometimes there can be contention and a lot of extra overhead, even just pulling the kernel. So I suspect there's actually low-hanging fruit in the async messenger thread that we could probably improve fairly dramatically. But yeah, 3 is definitely, and most people just stick with the default. And it's often the best.
Yeah, and that's why I actually like asked this question. I didn't realize that I had this kind of in the back of my mind that, okay, since up to 4 it performs pretty much the same, then that's what people get. But I didn't realize that the difference would be so dramatic. So I'm also wondering whether there is something. I'm not sure if it's quite low hanging, but something that is actually feasible to fix in terms of some state being shared unnecessarily on some log being just bounded upon to make this even just slightly better, because it just flats out, right? And I'm still kind of having a bit of a hard time wrapping my head around the normalization here, but I think the trend is clear. So
yeah. One thing, Ilya, last summer I was working on kind of the intersection of the OSD threading and the async messenger threading, and there were some advantages to doing things like implementing double buffering between those 2 layers to try to reduce the contention of the messenger threads, trying to grab the locks for the per shard queues in the OSD. I think there's probably some other things kind of that might be kind of making the async messenger threads, at least on the OSD side, less efficient than they should be. But I wasn't able to really finish it. I got stuck doing other things, so it is something I kind of want to get back to.
We've seen that it's also significant in like end results with trying the FAO write and read 4K. And from what you said, Ilya, earlier about the popularity of this config, I agree that it's not widespread, because I've tried to seek for some like people who mess around with this configurable, and it seemed that most people stick with the default. So yeah, I agree it has significant, and I don't know if there's something to fix there, but yeah.
When
so
you guys
with 3 threads, there's probably not. Yes, sorry, Mark. With 3 threads, it doesn't look like there's much to fix. But so again, it's just a question of priorities and where do we want to spend our time, like investing in Crimson Messenger and generally in Crimson seems like the path forward. But again, I just didn't expect the difference to be this dramatic.
on the x-axis, when you say CPUs, what does that mean exactly?
CPU cores used.
Fully used.
Allocated.
Allocated. How about actually consumed?
It's hard to test consumed with Crimson because it's busy pooling the CPU, so the CPU utilization is always busy.
Okay, so you're literally spinning 54 cores at the top end there.
Yeah. That's how the sister reactor. Inkshin, correct me if I'm wrong, but as far as CPU utilization, it should be.
Yeah, that's correct. And we also add more than, from the right side, we add more than 100 more cores. We tested
So the
with
reason
100 more cores.
The sort of zoom out reason for that is that in a normal Crimson configuration, those cores don't just do, those threads don't just do the messenger, they also do OSD work too. It's not like the async messenger in that there's a distinction between the thread pool used for the messenger and the thread pool used for everything else.
Sure.
So good scaling properties in the Crimson messenger is a lot more useful than good scaling properties in Classic.
Yeah. Okay. So here with the async messenger, you're just like, yeah, bumping up the number of async messenger threads versus Crimson's overall like thread reactors, rather. Is that right? I mean,
Yeah,
Crimson
both.
is the number of reactors, right?
Yeah, number of reactors. Yes.
Okay. Okay.
Yeah, so it's more meaningful to understand to prove that the current shared nothing implementation is working as expected, because at even 100 more cores, the behavior is still consistent. So I think that's the most important observation.
And those ping pong tests, do they need to go through a single reactor and then have like a crossbar splitting them to other reactors, or are those ping pong tests to individual reactors acting independently?
In different process. So different Crimson Messenger is in different process.
I think he's asking, when you service the response on the server side, does it need to cross to another reactor before going back? It's relevant because in a normal OSD, the message handling will typically come in at whatever reactor it comes in on. Then it needs to be farmed out to the reactor actually handling that placement group. Is that your question, Mark?
Yeah, exactly.
So no, in this case, they wouldn't
No.
be. They would be directly in and out. The same would be true of the async messenger as well.
Yeah, okay. Okay.
Just a note about the number of different kinds of threads in classical OSD. As Ilya said, we have 3 messenger workers. And by default on SSD, we have 16 TP OSD TP threads, the main workers, plus single bster KV sync thread, which is important for writes mostly. And now the question is improving scalability of messenger worth the effort? Because I wouldn't be surprised if we have a bottleneck somewhere else. I can recall that a typical vendor practice when deploying classical OSD on very fast NVMEs was to shard, to split the device and deploy a bunch of classical OSD instances on them. So let's say that we want to scale OSD 2 times. We need 6 threads of messenger, and how many TP OSD TPs? 32. Well, it might be simply not worth the effort.
Yes, that's a very simple aspect to test the messenger core scaling, and that's why we also tested the scaling property with OSD, but with a memory-based store. So that's 3. The messenger is just a simple test here. So that may not be very important compared with OSD scaling.
Well, I just wanted to say that a benefit coming from improved messenger scalability might be marginal till
I agree.
We improved other parts of OSD as well. And if other parts of OSD require similar scalability improvement, well, I would say we have Crimson OSD for this kind of purpose. So
yeah, and then on your with regards to just counting threads, I think the OSD has at least 2 messenger instances, right? So it's twice the number of workers for because you would have the kind of the front and the back instance, and there might even be a third one
I don't see that in the like if you look in GDB, I don't see like 9 instances of messenger threads. So I don't think so, Ilya.
Okay, so I guess I'm talking nonsense then.
No, that's true. Every messenger has its own threats. I don't think the Heartbeat messenger threads have very many of them, though. But they do exist.
Are they named differently, Sam? Because I can't recall seeing them.
I really don't remember. You'd have to look at the code.
We have.
But there's no mechanism that I'm aware of that would allow the async messengers to share threads. They have their own thread pools.
Yeah, and so then I would expect, just again based on I would expect 3 threads for the kind of client side messenger, 3 threads for the replication network, and then possibly the Heartbeat messenger might have the the reduced number, maybe it's defaulted to 1 or something, but I would expect like at least 3 different messenger instances.
There are 4, there are 4 messengers in classical OSD. Front client, cluster, and front heartbeat, back heartbeat.
So there are 2 Heartbeats. Okay.
Yes, I think we in total we have 12. We have dozen of messenger threads, but I guess that there is huge asymmetry, not only between the data shuffling, the jumbo messenger, let's call it that way, and Heartbeat messengers, but even between the public messenger, the one handling clients, and the one for talking to cluster. Maybe that would explain why Mark is seeing only public messenger threads.
Actually, there's a stat singleton concept. They might actually be sharing threads. I might be wrong. Not sure.
Yeah, I was gonna say I don't see
Anyway,
like a huge number of
it's
instances.
kind of a rabbit hole though in this context.
Yeah. I did put the our different messengers in the Ceph OSD.cc file that we create in the chat for anyone that wants to start going down that rabbit hole.
If you send terminating signal, let's say if you send stack fault to OSD, it should dump it should, in the summary of the printed by the signal handler, you should see the list of all threads.
Sure. Yeah. I mean, I just look in GDB, but
fair enough.
One thing I want to mention too, Radek, you had mentioned, maybe not wondering if like making improvements to async messenger isn't worthwhile. But what about in the context of both the clients and other daemons? I don't imagine that we're going to be able to port those to Crimson anytime, or to C* anytime soon.
That's fair point, but with clients are quite different when it comes to comparison with OSD. We assume, maybe that's wrong, not sure. We assume that a bottleneck at client is far less worse than a bottleneck in, let's say, OSD. As we tend to have far more machines for clients than we tend to have far more clients than OSDs.
Yeah, but on the other hand, a client can actually be a thing that is another daemon, a gateway handling God knows how many actual user workloads. The NVMe gateway is the primary example there.
That's a very good example. Yes.
Yeah, I think it's worth some time putting in at least a little effort into the async messenger, especially if there's low-hanging fruit that we could easily pick off.
Would it be possible? Just I have no answer. Just thinking very loudly. Wouldn't it be possible to settle the Crimson's messenger on top of, let's say, STD future. In other words, maybe even at higher abstraction, would it be possible for classical world to use Crimson Messenger?
I think fixing async is likely easier. Using C-star with classic is a huge pain. We've run into that with running Alien Store. They have different allocators and a bunch of other problems. I think you would find that to be not an easy retrofit.
Yes. Bringing C-star everywhere? No. That's for sure. But can we?
No, Radek, I mean, the messenger would have to allocate the messages. Like specifically the scenario you're describing, where you use the Crimson. Sorry, you can't port. I see what you're asking. You can't port. Standard future isn't a reactor. All it is a simple way of expressing this like future promise relationship. It's like 1% of the total amount of stuff you'd need to retrofit in order to run messenger.
Of course. It's just about actually. The future here is useful only from the point of view of interface. I mean, it should be similar to Crimson, to C-star's future. Yet, of course.
Yeah, it's not though. That's what I'm saying.
Oh, that's bad.
They have basically they don't have much in common.
Okay, so what idea is that?
It's more like an interface into which you could plug C-star's future.
Because internally, I think Messenger is all about event center, a reactor.
Sorry, what was that, Radek?
Well, this thought has been provoked by the observation that actually event center of ASIC Messenger is actually kind of a reactor.
Yes, that's true. So if you refactored Crimson's messenger and basically rewrote it from scratch to tolerate those two different run environments, yeah, maybe. But it would be a rewrite.
That's bad.
Yeah, it's really, really hard to abstract out something like a reactor. If you want to do that, you have to do something kind of like what SPDK does. You end up with a fairly complex set of callbacks. Doable, but
no, not worth the effort. I was hoping.
Well, it would be a significant amount of implementation overhead for Crimson. Also, I think Mark's probably right. It's probably the case that the scaling issues there are pretty fixable. And I do think it's worth fixing for the NVMe thing, if nothing else. Although I will point out that that would benefit from a C-star implementation of the. So, Mark, for context, the NVMe client is running inside of an SPDK reactor. So,
interesting. I didn't know that.
But the problem is that it's not. All of the Ceph parts are running in their own worker threads, and it's actually really inefficient. Ideally, we would have an objector that could run on something like C-star that could then be directly embedded into the SPDK reactor threads. If we did that, all we actually have to do is create a C-star environment for SPDK, which is possible, where you'd be running all of the SPDK callbacks in the C-star threads. It's a surprisingly flexible framework. SPDK is.
Yeah, and actually, C-star even now, out of the box, is integrated. Has integrated the DPDK, which is awfully similar to SPDK in my understanding. DPDK is just the idea in the domain of networking, while SPDK does something very, very similar in the domain of storage.
In this context, it's actually the reactor stuff that's relevant. So that's shared between both projects.
Yes, but the point is that if a project already uses the PDK, it should be very, very straightforward to extend it to SPDK.
So one somewhat depressing topic there is, as far as I know, Intel has let go all of the SPDK developers. Yingxin, I don't know if you know any more about that, but
I think so.
yeah. Oh, we gotta go, but yeah, IOU ring
Yeah.
seems like maybe the next way to go. I don't know.
Cool. So I'll probably have to cut it out because people need to move to core. But again, thanks for joining and have a nice day.
Bye, guys.
Thank you. Bye.
Thank you.